In this video, we will continue our case study on nitrifiers. After understanding the metabolism of nitrifiers, we can now move on to stoichiometry and kinetics, two concepts that bridge microbiology and engineering. We can derive the catabolic and anabolic equations using balancing principle. Then by obtaining the biomass yield coefficient, we can combine these two equations into one overall metabolic equation. This overall equation tells us the ratio between substrate and products. For example, for every 1 mole of ammonia consumed, about 2 moles of oxygen and 0.085 moles of CO2 are required. In return, around 0.017 moles of biomass and 2 moles of proton are produced. These ratios tell us exactly how much substrate is needed, which directly connects to the operational cost. Next, we want to understand kinetics, or how fast this reaction occurs. Each substrate has its own consumption rate, but they are not independent. The slowest rate becomes the limiting rate, the bottleneck that determines the maximum volumetric capacity of the reactor. And that capacity determines how large the reactor needs to be, which directly affects the investment cost. Stoichiometry helps us understand what nitrifiers need from the cell's perspective, but in practice, we can only control the process from the reactor's perspective. This brings us to physical transport process. Good mixing is essential and can be achieved using mechanical mixers or aeration. Mass transfer is also a key factor. It determines how easily substrate reach the cells. Oxygen is often the limiting factor in biological wastewater treatment because oxygen is in high demand for biological conversion, but its solubility in water is very low. The size of bioaggregates also plays a major role. Larger aggregates suffer from more mass transfer limitation. For example, oxygen diffuses much more easily into loose flux than into thick biofuels or granules. Mass transfer illustrates that only a small fraction of the oxygen we supply through aeration actually reaches the biomass. So mass transfer efficiency becomes crucial when determining aeration demand, how much air needs to be supplied. And aeration demand again links directly to operating cost. As we have discussed before, biomass retention is another critical aspect in environmental biotechnology. For nitrifiers, retaining biomass helps increase their concentration in the reactor, which in turn increases the volumetric nitrification capacity. This happens because biomass retention allows us to decouple the hydraulic retention time HRT from the solids retention time SRT. We can achieve biomass retention in two main ways: through physical separation or through biofuel formation. By increasing the volumetric capacity, we can design a smaller reactor, which helps reduce the investment cost. Now that we have covered conceptual aspect, let's look at a reactor design example to deepen our understanding. Imagine we are now given a task with treating wastewater containing 100 mg per liter of ammonium nitrogen with a flow rate of 100 cubic meter per hour. To meet this goal, we need to design a nitrifying bioreactor capable of sufficient conversion. Our main design questions are: how much aeration do we need, and how large should the reactor be? These two parameters relate directly to operation and investment cost. Note that the numbers and calculations used in the example have been simplified for clarity. From the nitrifier metabolic equation, we know how much substrate is required for a given amount of ammonia. With 100 mg per liter ammonium nitrogen and a flow rate of 100 cubic meter per hour, we can calculate the amount of necessary substrate and resulting products. For instance, the required oxygen is about 45.7 kg per hour, and the CO2 needed is around 2.67 kg per hour. Let's choose a continuous flow well-mixed reactor that supports flow growth for our design. Our first design requirement is to meet the growth needs of nitrifier. they require a minimum SRT of about 2 days. Here we will use 4-day SRT to ensure steady growth and a low effluent ammonia concentration. Once we set the SRT, it determines the growth rate of nitrifier and can be used to calculate the reactor size. Without biomass retention, HRT is equal to SRT, so the reactor size is determined by the HRT and the influent flow rate. However, this design leads to a very large reactor, so we will apply biomass retention to reduce the required volume. As we have learned, biomass retention is a powerful way to increase biomass concentration and therefore volumetric capacity. This increase isn't unlimited. In this example, a 10-fold increase in biomass concentration is feasible, giving a 10-fold increase in volumetric capacity. As a result, the reactor volume can be reduced to 1/10 of the original size. Next, we define the reactor's height and surface area, which are important for mass transfer. Based on these, we can calculate the aeration requirement. Starting with oxygen, stoichiometry tells us how much is needed biologically. After performing mass transfer calculation, we find that an aeration rate of 1750 cubic meter air per hour can satisfy the oxygen demand. Now let's look at CO2. At the same aeration rate, only about 1.26 kg per hour of CO2 can be supplied through the air, which isn't enough. Therefore, we need to supplement CO2, for example, by adding bicarbonate to the reactor. With this calculation, we can now determine the total aeration demand. Once we know both the reactor size and aeration demand, we have successfully completed the reactor design. Let's summarize the reactor design process. It begins with the goal of treating wastewater containing a specific amount of ammonia. We need to design a nitrifying bioreactor to achieve that target. Reactor design requires two key parameters: aeration demand, which affects operation cost, and reactor size, which affects investment cost. To determine aeration demand, we start by calculating the biological requirements for oxygen and CO2. Then, using mass transfer calculation, we determine the actual aeration needed, which depends on the reactor size. The reactor size, in turn, depends on how fast the conversion can occur, governed by the limiting process rate inside the reactor. If we step back, we can see how engineering design is deeply connected to microbiology. Aeration requirements is linked to stoichiometry. Reactor size is linked to kinetics, and both stoichiometry and kinetics are linked to metabolism, which is what we learn from microbiology. Through this case study, we can see how all the concepts from the first module come together in the example of nitrifier. This integrated framework can be applied to study any environmental process, and it forms the foundation of this course. In the following lectures, you will see more examples and applications that build on this framework and the knowledge you have developed here.